right, let's do another one. You feeling confident? I would suggest trying to solve this on your own and then coming back and checking to see how you did or where you got stuck. I am going to give you a little pointer though. We've been dealing with pressure for those last couple ones. This one, you're going to calculate the free energy change for the same reaction at 875 Celsius in a 5-liter mixture containing 0.1 moles of each gas. So we're going to be looking at concentration here, and make sure you remember how to find molarity, what that unit is, and seeing if you can solve this. So pause the video. All right, well, let's look and see. Molarity, or concentration, remember in our brackets, molarity is moles over liters, or moles per liter. So it tells us that we have 0.100 moles of each gas and 5 liters of it. So if I do 0.1 divided by 5, I have 0.02 of each. It says of each of my gases. This is my concentration. So now we can set up our Q, our reaction quotient for the concentration. Again, we're going to do products over reactants. So let's do I need my concentration of H2 cubed times the concentration of N2 all over concentration of NH3 squared. Okay, and we know that we have this is the concentration of each of those, 0.02. So let's just do 0.02 cubed times 0.02 over 0.02 squared. All right, let's solve for this. Let's do 0.02 cubed times 0.02 divided by 0.02 squared. I got 4 times 10 to the negative 4th. That's my Q. Okay, now let's plug in. We know that delta G for non-standard is equal to delta G naught, our standard, plus RT natural log of Q. So we should be given, here's our delta G, 33 kilojoules per mole plus 0.00831 kilojoules per Kelvin mole. That's our R. Our temperature, 875 degrees Celsius. Ooh, 875 degrees Celsius plus 273. 1148 Kelvin times the natural log of Q, our 4 times 10 to the negative 4th. Okay, let's do our calculator work. Let's do the natural log of 4 times 10 to the negative 4th, times that by 1148, times that by 0.00831. Then we're going to add that to 33 to get negative 41 point, let's see, 1 decimal point, 41.6 kilojoules for our delta G. So notice here we went from having a positive delta G where it was non-spontaneous to under these conditions, we now have a negative. We have a spontaneous reaction. How did you do? Did you get it? I bet you did, because you're awesome. All right, let's do another. All right, let's look at another problem. This one, it's written kind of funky. I'm just going to rewrite this. Let's say I've got calcium carbonate. Decomposes to form calcium oxide, solid, plus CO2, gas. Then we have a delta G naught, so it gives us free energy. A standard state is positive 131.1 kilojoules. Okay, so notice that down here, we're given the pressure of CO2 is not at 1. Okay, so we know that it's not at standard state conditions. Now, one thing that is super important that we need to know and remember is that when we are doing the quotient, the reaction quotients, where we did products over reactants and looked at these different pressures or different concentrations than the norm, we only include, especially when we're looking at pressures, we only include reactants and products for only include gaseous reactants, sorry. Reactants and products for pressure. There isn't a pressure value given to solid reactants or products. So we only include the gaseous reactants and products for pressure when we're calculating that Q. So for pressure, we do products over reactants. So since we're only given the partial pressure of 0.033 atm, that would be our CO2, and it's not squared or anything, over nothing. So our Q is simply this, which is kind of nice. So now we can plug it into our delta G on T natural log of Q. So we're given our Gibbs free energy at standard state. So delta G at non-standard state is equal to plus 131.1 kilojoules plus 0.00831 kilojoules per Kelvin mole. Our temperature tells us 298. And then the natural log of 0.033. So we saw at standard state that this was a non-spontaneous reaction. Let's see what happens in this non-standard. Let's do the natural log of 0.033 times 298 times 0.00831. And then we're going to add that to 131.1. And we get 122 point and then to 1.7 kilojoules. So again, still non-spontaneous in the forward direction. All right, let's keep going and doing some more practice problems. You're doing so good, and these concepts really stick when you do the practice. So let's calculate delta G at 298 under the conditions below. So we've got our mercury plus oxygen to yield mercury oxide, and we're given the pressures of the mercury and the oxygen that are in the gaseous states, obviously not for solid because it doesn't apply. So these are under non-standard states of pressure. In addition to solids not being in the reaction quotient, so pure solids and pure liquids, they drop out of the reaction quotients. All right, so Again, this is kind of a mess, so I'm going to just rewrite this real quick. 2 Hg's gas plus O2 gas react to form 2 HgO solid. Okay, so we've got the delta G naught, so that gives us free energy. Its standard state is negative, so it is spontaneous in the forward direction. So let's see if that happens to change when we have different pressures for our mercury and our oxygen. So to find our reaction quotient, and we're using pressures, we're going to do products over reactants. And since we said the solids are not applying, we're just putting nothing, 1 over, because we're not even using this. So, but that still is products over, let's do our reactants. So we do have to do the pressure of mercury squared times the pressure of oxygen raised to the power of 1. So 1 over the pressure of mercury, we said was 0.025 squared times the pressure of oxygen, 0.037. Now let's do our calculator work here real quick. So I'm going to do 1 divided by 0.025 squared times 0.037. And I should get the big number, 43243.2. Okay, so this is our Q. All right, now we just need to plug in to our delta G. We know that delta G is equal to our delta G at standard state, the negative 180.8 kilojoules, plus our R, 0.00831 kilojoules per Kelvin mole, times T, we were told up above, it's 298, times the natural log of, our big number here, 43243.2. All right, let's work this out. Natural log of 43243.2 times 298 times 0.00831, and we're going to add that to our negative 180.8. And this delta G, that non-standard state, so we've got a 54.4 kilojoules, still a spontaneous reaction in the forward direction. It was negative 180, and then we changed the conditions, still spontaneous at a negative 154.4 kilojoules. All right, let's look at this. Hopefully these practice problems are getting easier for you. So let's look at a system that's in equilibrium. That means that our reaction quotient Q is equal to K. Our delta G is equal to 0. So we can take that previous equation where we said delta G was equal to, gives us free energy at standard conditions plus RT natural log of K. But if we're making delta G 0, again, this is at equilibrium, we can set that equal to 0. Then we can subtract RT natural log of K from both sides, which gives me delta G equals negative RT natural log of K. And then we can solve for that K, that equilibrium constant, by saying K is equal to the opposite of the natural log, which is Euler's number. And this is on your calculator. Well, it depends, I guess, what calculator. But if you hit second natural log, it's e to the x power. This is Euler's number base. So then we would have to the negative delta G is standard divided by RT. Now, again, this is at equilibrium, and we've been talking about that equilibrium constant. Sometimes it's expressed as KEQ. In future chapters, we're going to be looking at lots of different equilibrium constants, but we've been looking at Q, right? And we said if Q is equal to K at equilibrium, but we've been looking at Q for concentration. So we can also have K for concentration, K being equal to Q, the constant for pressure. So these are important to know. If we are at equilibrium, Q is equal to K, and then we would rearrange this equation, we can solve for K. So if K is greater than 1, Gibbs's free energy is less than 0, so it is spontaneous in the forward reaction. And with that K being greater than 1, we're having products are more abundant at equilibrium. So the forward reaction is favored. There are more products than reactants. If K is less than 1, G is greater than 0. So this is not spontaneous in the forward direction, but it would be in the reverse direction. But what that's telling us is that the reactants are more abundant at equilibrium. Again, the rates are not different on these, right? Because we're at equilibrium, so the rates are the same. But since this is greater than 0, it's non-spontaneous in the forward direction. So that means that the reverse direction or reaction is favored. And again, there's more reactants than products. And if they're equal, K is equal to 1, G is equal to 0, we know that we have reactants and products are equally abundant, right? That our products over reactants, if the K is equal to 1, that we have equal amounts of both. All right, let's look at this. What is the value of K for this aqueous reaction at 298 Kelvin? So we're not even given, a real true reaction. But if we go back and we looked at just that previous slide, we know that we can find K, that reaction constant. K is equal to, again, Euler's number, the opposite of natural log, raised to the negative delta G at standard conditions over RT. All right, so let's plug in what we know. K is equal to E raised to the negative 12.56. Well, I'm going to do a big bracket here and then a little bracket. There we go. 12.56 over, we know R is 0.00831 times, we know our temperature is 298 Kelvin. We're going to do that, and then the big bracket. Now let's simplify this. So let's do our 12.56 divided by, I'm going to put in parentheses, 0.00831 times 298. So I got 5.0719, so it's to e to the negative, right, 5.0719. Now K is equal to, again, we're going to do the second ln is what I did, or it's e to the x. Maybe you just have e to the x button, but it should look like this. And then I'm going to do the negative, and then I'm going to do, for me, I'm going to do answer. I can do second answer and just type that in. And I got 0.00627. So this K value, 0.00627, and it has no units. What this is telling me that this K is much less than 1. So it's a small K, which means there are more reactants than products. All right, so we have this one and we have one more sample problem after that. You guys are doing such good work. Keep it up. I also suggest, pausing the video and working ahead and then checking to see if you're doing it right. So let's look at this. We have the decomposition of a metal oxide into its elements where M is a generic metal. What is the standard change in Gibbs's energy for the reaction as written in the forward direction? Okay, so we're looking at standard change. And we know that to do that, to find our, that's a G, standard G for our reaction is just the sum of the G products minus the sum of the reactants. Again, this is a standard state. So here we're given our standard state. Let's look and see here. Our products, we have a metal and we have our oxygen. And notice that the metal and the oxygen, oh yeah, when those are elements that are, again, found naturally in nature, they're zero. So I have 0 for my products minus my reactant, M2O. M2O is told that it's negative 7.10. And this is kilojoules per mole. So minusing a negative, that's going to give me a delta G of my reaction of 7.10. So we have a positive value here, telling me that this is non-spontaneous. All right, now let's find K. What is the equilibrium constant of this reaction as written in the forward direction at 298 Kelvin? So again, we know that our K is equal to Euler's number, the opposite of that natural log, to the negative delta G over RT. Okay, and then we're just going to say that that's equal to E to the negative. We just found our delta G was 7.10 over 0.00831 times 298. Let's simplify that, and we should get, let's see, 7.1 divided by, I'm going to put in parentheses, 0.00831 times 298, close that parenthesis, 2.87, so that's equal to E to the negative, because we have that negative on the outside, 2.87. So now I'm just going to do second natural log, or remember that E to the X of, hold on here, negative answer, close the parenthesis, and I got 0.0568, I guess that would be 569, so let's see, so that is equal to 0.0569, which is very small, right? It's much less than 1, so 0.0569. And so now, what is the equilibrium pressure of oxygen over M at 298 K? So now we want to find the equilibrium pressure of oxygen. So remember we said the equilibrium pressure, or I'm sorry, the constant that we find. The constant is equal to the partial pressures of, we'll say, pressures of products over the partial pressures of reactants. So we just found that K value. So now we just need to say, okay, well that 0.0569 is equal to the partial pressure of products. So we have O2 raised to the 1/2 times, that's interesting, our other product is a solid. Nope, we don't use it. Okay, over our reactant, also a solid. So actually, when we find this, we're just going to say 0.0569 is equal to the partial pressure of oxygen raised to the 1/2. So we get rid of a half exponent by squaring it. So I'm going to square this, and that gets rid of that, which means I have to square this side. So let's do 0.0569 squared, and we get the partial pressure of oxygen. Oh, I don't know, I did that. O2, partial pressure of oxygen is equal to 0.0032 ATMs, atmospheres, for our final, here, 0.0032 ATMs. All right, we have one more. All right, let's see what we have here. We want to determine the equilibrium constant. Okay, well, in order to find the equilibrium constant, it is our Euler's number, the opposite of natural log, raised to the power of the opposite, delta G over RT. So interestingly, we don't know what delta G is. We weren't given it. But what we were given was H, our enthalpy and entropy. So we can find Gibbs's free energy. And if you remember, delta G is equal to delta H minus T delta S. So let's find G so we can plug it into this equation to find our equilibrium constant. All right, so we're going to say that our delta G is equal to our delta H, so negative 94.9 kilojoules, minus our temperature in Kelvin, 549 Kelvin, times delta S. Again, remember, delta S is in joules, so let's make this into kilojoules. So times, it's a negative 0.2242 kilojoules. Okay, let's simplify this. So I'm going to do 549 times a negative 0.2242. This is a negative 123.0858. We won't simplify till the end. So negative 94.9 minus a negative 123. Let's plug that in. Negative 94.9 minus a negative 123.0858. And I got 28 point delta G, and we are to the 10th here when we're adding and subtracting, 28.2 kilojoules. Okay, that's delta G. That's great. Now we can plug delta G into our equilibrium constant expression. So K is equal to, again, Euler's number, the opposite of natural log, to the negative. We're going to plug in our 28.2 kilojoules over R 0.00831 times our temperature, 549 Kelvin. All right. Let's use our calculator here, and we're going to do 28.2 divided by 0.00831 times 549. Close that parenthesis. Now we're going to do e to the negative of the answer that I just got, and 0.0021 would be my K, 0.0021, another small K for my reaction constant, my equilibrium constant. Again, showing that it's reactant favored, which makes sense because my delta G is positive, so it's endothermic. So it's going to be, non-spontaneous. Delta G is non-spontaneous, not endothermic. And therefore, it will be non-spontaneous in the forward direction, spontaneous in the reverse direction, so it is going to be pushing back towards those reactants. Well, that completes our notes on thermodynamics. I highly suggest that you practice, practice, practice. I look forward to seeing your notes in the Dropbox and hope that you are feeling confident about where you're at with all of these thermodynamics. There are a lot of equations and there's a lot to absorb with this. So look over your notes, do some more practice problems, look at those, the odd numbers, solutions, so you can do more practice from the book or wherever.